Hey everyone, ready for another deep dive? Today we're tackling how AI is learning to solve math problems, but not just simple arithmetic.
Yeah, we're talking way beyond that. This is about AI that can reason through multi-step problems, almost like a human would.
It's like AI is becoming a mathematician, using logic and code to crack those tricky equations.
Exactly. And get this, they're even learning to write Python code to help themselves solve problems.
Whoa, AI writing code. Now that's something I gotta hear more about.
Oh, it gets even cooler. Our source material is a research paper, a bit of a dense one though, building math agents with multi-turn iterative preference learning. But don't worry, we're here to break it down.
Okay, good, because that title alone already makes my head spin a little.
Right. But the core idea is that these AI agents, as the paper calls them, are learning through a method called RLHF, which stands for Reinforcement Learning from Human Feedback.
So basically, they're learning by doing and getting feedback along the way.
You got it. But there's a unique twist here. These agents are interacting with external tools, like a Python interpreter, to get feedback and improve your strategies.
So it's not just about internal reasoning. They're actually using tools, like having a calculator at their disposal.
Yeah.
That's a game changer.
It really is. And to really grasp how it works, let's visualize it. Figure 1 in the paper shows the agent going back and forth, reasoning, writing code, getting feedback almost like a human programmer, but with an AI brain.
Hold on, back up a sec. The AI is actually writing code. That's wild. How does it even know what code to write?
It uses its internal knowledge, what it learned in its initial training, to guide its coding decisions. It's using code as a tool to boost its reasoning, not just copying from somewhere.
So it's thinking strategically about how to leverage those tools. Pretty impressive.
And the feedback isn't just right or wrong either, it's more nuanced than that.
Oh. So how does this feedback system work? What are the AI agents learning from?
They're getting relative feedback, which means they learn by comparing different solutions and figuring out which is better based on that feedback.
So it's like having a teacher say, yeah, you got the right answer, but there's a better way to think about this.
Exactly. This constant feedback loop helps the AI refine its reasoning over time. It's not just about the destination, it's about the journey of problem solving.
I'm with you. But here's a thought. What if the AI stumbles onto the right answer by accident? Like, the logic's flawed, but the final number matches.
Yeah, you've hit on a major challenge. False positives. Just like a student might fluke a right answer, AI can do that too. And this is something the researchers addressed directly.
Okay, I was hoping they'd thought of that. So how do they tackle these sneaky false positives?
They've got two types of reward models to evaluate solutions. ORMMs, outcome supervised, and PRMs, process supervised.
Whoa, hold up. Lots of acronyms. Break that down for me.
Sure. ORMMs focus on whether a solution is truly correct, not just if the final answer is right. They look for consistency and logical coherence in the AI's reasoning.
So ORMs are like a super smart answer key, making sure the AI isn't just getting lucky. What about the PRMs then?
PRMs are like the teacher grading each step of the student's work, giving feedback along the entire reasoning process, not just at the end.
Ah, I see. It's like having a tutor guide you through every step, catching those little errors before they snowball.
Exactly. And this focus on process feedback is what sets this research apart from the traditional AI training methods.
Okay, this is all starting to make sense. But before we dive deeper into the training, how does this research differ from those deep reinforcement learning techniques we often hear about?
Great question. Deep RL methods like PPO can be powerful, but they're resource heavy, requiring tons of data and computing power. This research explores a more efficient approach called direct preference learning.
Direct preference learning, huh? Sounds intriguing. How does that work?
Think of it like teaching chess. Instead of having someone play thousands of games to learn, you show them good moves versus bad moves directly. That's the essence of it, faster and more targeted learning.
Ah, so it's about learning from expert demonstrations, not just trial and error.
Precisely. And to make it even more efficient, this research introduces a new twist: multi-turn direct preference learning.
Okay, you've definitely piqued my curiosity now. Why is this multi-turn aspect so important for these math agents?
Well, imagine trying to understand a chess game by only looking at the final board. You'd miss all the crucial decisions that led to that point, right?
You'd have no clue about the strategy or the individual moves that matter.
Exactly. Multi-turn learning allows the AI to learn from the entire sequence of actions, not just the final result. Crucial for problems that involve multiple steps.
Gotcha. It's like watching the entire game, not just the highlights reel. This helps the AI understand the logic behind each step,
I
right?
think nailed it. And that's what makes this multi-turn learning so groundbreaking. It's a way for AI to learn much closer to how we humans do.
I'm already blown away by all this. But I'm also curious, how do they actually train these multi-turn agents? It sounds incredibly complex.
It is complex, but they've created a specific algorithm for it. Online Iterative MGSHF. Don't get bogged down by the jargon, but basically it guides the AI through cycles of generating solutions, getting feedback, comparing approaches, and refining its internal model as it learns.
Okay, let's break down this process step by step. I'm ready to be amazed.
So first, the AI generates a bunch of different solution attempts for a given problem. And to make things interesting, there's some randomness thrown in just to shake things up a bit.
So they're encouraging the AI to think outside the box, not just stick to the same old routine.
You got it. Then, out of those solutions, the best ones are picked based on either human feedback or how well they score on those reward models we talked about, the ORMs and PRMs.
Right, so the AI gets rewarded for solutions that either a human likes or that pass those stricter evaluation tests. Makes sense.
And then comes the cool part, the learning. The AI compares those chosen solutions to the ones that were rejected, figuring out what makes a good solution good and a bad solution bad.
So it's constantly learning and refining its understanding of the problem and the best way to approach it.
It's a continuous process of improvement, just like a human student studying and practicing.
This is all fascinating, but does it actually work? Like, do these multi-turn agents really outperform other AI systems out there? That's the real test, right?
That's the big question, and based on the paper, the answer is a resounding yes. They tested these agents on two well-known benchmarks, GSM8K and MATH, and the results were really impressive.
Okay, I'm all ears. How much better did they perform? Give me the numbers.
Hold on tight.
Yeah.
Table 1 in the paper shows the breakdown, and the numbers are pretty compelling. First of all, we see that the agents using tools, specifically Python code, completely outperformed those using just chain of thought.
So basically, giving the AI access to those tools was a huge advantage. What exactly is chain of thought, by the way?
It means the AI is relying solely on its internal reasoning, no code execution or anything. Chain of thought models can be pretty powerful, but for these tougher math problems, using external tools is a game changer.
Right, like having a calculator versus doing everything by hand. It's a huge difference.
Absolutely. But what about the actual learning methods? How did those multi-turn preference learning techniques, MDPO and MKTO, measure up? Did they live up to the hype?
Yeah, that's what I'm really curious about. Did they actually deliver?
They did. They showed a big improvement over standard supervised fine-tuning, which is often called SFT. We're talking accuracy boosts of several percentage points on both GSM8K and MATH.
Wow, that's a significant jump, especially in AI, where even small gains can be a big deal. Quick reminder, what is SFT again?
SFT is basically the traditional approach to AI training. Feed the model tons of labeled data, in this case, math problems and their solutions, and it learns to imitate those solutions. It's a good starting point, but it doesn't always cut it for more complex reasoning.
So it's like giving the AI a textbook and hoping it figures everything out on its own. While these preference learning methods are more like having a teacher guide and support the AI's learning.
That's a great way to put it. And these new methods didn't just outperform SFT, they consistently beat other RLHF approaches too, including one called RAFT, or Reward Ranked Fine-Tuning.
So they're even better at learning from human feedback than other cutting-edge methods. Color me impressed. But what's the secret sauce? Why are MDPO and MKTO so effective?
One key factor is their ability to learn from both positive and negative feedback. RAFT mainly focuses on copying the right solutions, but these DPO and KTO methods go a step further. They learn from mistakes and incorrect reasoning paths as well.
Like the saying, you learn more from your failures than your successes. It gives you a more well-rounded understanding of what works and what doesn't.
Exactly. And this ability to learn from mistakes is essential for tackling these multi-step problems so that the AI can pinpoint where it went wrong and adjust its approach.
Okay, all this is incredibly promising, but hold on a sec. Are we saying these multi-turn agents have reached the pinnacle of math-solving AI? Is this as good as it gets?
Not quite. While the results are impressive, we have to remember these agents are still learning from a limited data set. Preference learning isn't magically injecting new math knowledge into the AI's brain.
So it's more about helping the AI become incredibly efficient at applying the knowledge it already has.
You got it. These agents are masters at using what they know, but their potential is still limited by the data they've been trained on.
Makes sense. It's like saying, this chess AI can beat any human, but it can only play the openings it's been trained on.
Another perfect analogy. The researchers also looked at something called pass at n accuracy, which basically tells you how likely the AI is to find the right answer within a certain number of tries.
So it's like saying, if we give the AI 5 chances, what are the odds it'll solve the problem at least once?
Exactly. And what's interesting is that this preference learning approach only seemed to boost the pass at n score when n was relatively small.
Hmm, interesting. What does that tell us about how these agents are learning?
It suggests that preference learning is really good at helping the AI pick the absolute best solution out of the options it already knows. But it doesn't necessarily make the AI drastically better at coming up with completely new solutions.
So it's like fine-tuning a search engine. It might not expand the total number of websites out there, but it gets a lot better at ranking the most relevant ones at the top.
You're killing it with these analogies. That's a great way to put it.
Okay, all this talk about agents has me wanting to see them in action. Can we look at some specific examples from the paper to get a feel for how they tackle these problems?
Absolutely. Let's dive into some case studies that show both the strengths and weaknesses of these AI agents. One interesting one involves result checking, which is a common technique in math.
Right, like double-checking your work to make sure you didn't make any careless mistakes.
Exactly. Example one in the paper shows how even when they try to be careful, AI agents can sometimes get the right answer for the wrong reasons.
Uh-oh, that sounds a little worrisome. How does that happen?
Imagine the AI is working through a multi-step problem, writes its code, runs it, and boom, gets the right final answer. Seems like a success, right?
Yeah, so what's the problem? It got it right, didn't it?
It did, but if you look closer, you might find the AI made a logical error somewhere along the way. Maybe it used the wrong formula or misinterpreted some information, but by pure chance, those errors ended up canceling each other out, leading to that correct answer.
Oh, that's sneaky. Like when you accidentally subtract instead of add in a problem, but then make another mistake that magically fixes it. You get the right answer, but your understanding is completely off.
That's exactly the kind of scenario the researchers are grappling with. These false positives can be tricky to catch, which is why we need those more sophisticated reward models that go beyond just checking the final answer.
Right. We need to make sure the reasoning is solid at every step, not just that the AI spat out the right number.
Exactly. And that's where those ORMs and PRMs we discussed really shine. They're like those vigilant teachers who can spot those logic errors and guide the AI towards a true understanding of the problem.
Now, I vaguely remember a visual in the paper showing a really challenging message the AI might receive from the Python interpreter. Was that figure 3?
You've got a sharp memory.
Yeah.
Yes, figure 3 gives us a peek behind the curtain, showing us that it's not always smooth sailing for these agents. Sometimes the code they write is, well, let's just say it needs some work.
So, not exactly elegant, perfectly optimized Python code.
Not always. Remember, they're still learning. Their code can be clunky, inefficient, even have errors. And when that happens, the Python interpreter might throw back a cryptic error message that the AI has to decipher.
Okay, that sounds frustrating both for the AI and the researchers. How do they handle those situations?
This is where the robustness of the training process really shines. The AI has to learn to interpret those messy error messages, figure out what went wrong, and fix its code. It's a valuable experience that pushes it to think critically and understand how code really works.
It's like when you're debugging your own code. Super annoying, but often helps you understand the code better in the long run.
Exactly. These challenges are what make this research so exciting. We're not just training AI to solve textbook problems, we're training it to think like programmers, to debug, to learn from its mistakes.
This is mind-blowing stuff. Seeing what these AI agents can already handle makes me wonder what they'll be capable of in the future.
That's what's so groundbreaking about this research. It's not just about acing math tests, it's about developing new techniques and frameworks that could revolutionize how we train AI for all sorts of complex tasks.
It feels like we're witnessing the early stages of a technological revolution. Exciting and a bit mind-boggling all at once.
I couldn't agree more. Ready to delve even deeper? We haven't even touched on those ablation studies yet, which reveal some really cool insights into the effects of different training choices.
Bring on those ablation studies. Let's uncover some more of those secrets.
Yeah.
Okay, let's dive into those ablation studies. What kind of tweaks did the researchers make, and what did they find?
Oh, they really got into the nitty-gritty of the training process, testing out all sorts of different parameters and choices. And it turns out even small adjustments can have a big impact on how well these math agents learn.
So it's like fine-tuning a race car, looking for those tiny adjustments that can shave off precious seconds. What was the first thing they explored?
Well, they took a closer look at KL regularization, which, if you remember, is all about striking that balance between letting the AI explore new ideas and making sure it doesn't stray too far from what it already knows.
Yeah, it's like giving the AI a bit of freedom to experiment, but keeping it on a leash so it doesn't run wild. What did they discover about fine-tuning this KL regularization?
They found that a moderate level of KL regularization worked best, too little, and the AI's exploration became kind of random and unproductive. Too much. And it basically stifled the AI's creativity, preventing it from trying new things and improving.
So like Goldilocks, it's all about finding that just right level. What happens when they hit that sweet spot?
When they get it just right, the AI can explore new possibilities while still staying grounded in its existing knowledge. This leads to much smoother, more consistent learning and improvement.
It's like having a GPS that can guide you to your destination, but also allows you to take some interesting detours along the way.
Exactly. And speaking of exploration, another ablation study focused on different sampling strategies. Turns out a technique called mixture sampling consistently outperformed just using the latest model to generate solutions.
Okay, remind me, what's mixture sampling again?
Mixture sampling is all about keeping things diverse. So instead of just learning from the most recent version of itself, the AI also uses solutions from earlier versions during training.
Ah, so it's like adding a dash of old school wisdom to the mix. It keeps things fresh and prevents the AI from getting stuck in a rut.
That's a great way to think about it. By incorporating those solutions from different stages of training, mixture sampling makes sure the AI is exposed to a wider variety of approaches and ideas, which ultimately helps create a more adaptable and well-rounded model.
Makes sense. It's like cross-training for athletes. It helps them develop a more diverse set of skills.
Another fantastic analogy. This finding really underlines how important data diversity is in AI training. It's not just about having lots of data, it's about having a diverse and varied data set.
Now, earlier we talked about that concept of NLL loss and how it can be a bit tricky. Did these ablation studies offer any more clarity on when it might be helpful or even potentially harmful?
They did. And the results were intriguing. It seems like NLL loss can actually give a performance boost to models that were seriously underfitting.
Meaning, those models that weren't learning as much as they could from the data.
Exactly. In those cases, adding in NLL loss gave them a little kickstart, helping them learn more effectively. But here's the catch. For models that were already learning well, NLL loss often made things worse.
Oh, so it's a bit like giving caffeine to someone who's already wide awake. Might not be helpful and could even backfire.
Precisely. It seems like NLL loss is a tool that needs to be used carefully and thoughtfully, taking into account how the model is learning. The researchers also discovered that certain training choices, like slowing down the learning rate and using something called on-policy sampling, could help prevent some of those negative side effects of DPO. Specifically, it helped prevent the AI from lowering the chances of picking good solutions.
Wait, why wouldn't we want the AI to favor good solutions? That seems counterintuitive.
You'd think so, right? But sometimes when the AI focuses too much on just those preferred solutions, it can get a bit narrow-minded in its approach.
Ah, so it's like studying for a test by only reviewing the questions you already got right. You might miss out on really understanding the concepts behind the ones you got wrong.
Another great analogy. By using techniques like a slower learning rate, we can help the AI take a more balanced approach to learning, considering both its successes and its mistakes.
Which brings us back to that theme of finding the right balance. It seems like that's crucial throughout this entire research paper.
Absolutely. And I think these ablation studies highlight a broader point about training AI. It needs a holistic approach. You can't just tweak one little thing and expect miracles. You need to understand how all the different elements interact and work together.
It's about carefully guiding and shaping the AI's learning process to build a truly robust and capable system.
Well said. This research is a testament to just how much progress is being made in AI. And it's not just about math. These techniques and insights could be applied to so many other fields, from understanding and processing language to designing and controlling robots.
The possibilities really are endless. It's an incredibly exciting time to be following this field. So as we wrap up our deep dive today, what's the one key takeaway you want our listeners to walk away with?
For me, it's the power of multi-turn preference, learning to bridge the gap between human and artificial intelligence. We're moving beyond just programming AI to mimic us. We're starting to understand how to actually teach it to learn and reason more like we do.
It's like we're giving AI the tools to become more like us, to think more like us, to solve problems more like us. That's both incredibly exciting and a little bit daunting, isn't it?
It is, and it leads to a final thought-provoking question for our listeners. If these math agents are already this capable, what other complex human tasks could they master in the future? Could we see AI helping us design groundbreaking algorithms, write scientific papers that revolutionize our understanding of the world, or even compose beautiful symphonies? The possibilities are truly mind-boggling.
They really are. I think we've given our listeners plenty to ponder today. Until next time, everyone, keep those mental gears turning.